We can also explain the property of the kinetic and potential energy, or the behavior of the kinetic and potential energy in the simple harmonic motion using the motion diagram like this, and also the energy diagram like this. At the maximum displacement at this point, here x is x max, so the acceleration a has a maximum value also, and at this point we know that v is equal to 0. So if we look at the energy diagram, you can see that the kinetic energy is 0. The blue bar represent the kinetic energy and the orange bar represent the potential energy. We can see that here the kinetic energy is 0, the potential energy is maximum, 100% of the total energy, and the red bar represent the total energy, and the potential energy is equal to the total energy. In contrast, we have that at the equilibrium point, here x is equal to 0, and the velocity of the object has maximum value. So if you look at the energy diagram, you can see that the kinetic energy is maximum here, while the potential energy is 0. However, the total energy of the system is still constant. And at the other point, for example, here is a position that x is equal to the minus a. So we have the maximum potential energy again at this point, and the 0 kinetic energy at this point. And if you go back to this position, x equal to 0, you have the maximum kinetic energy again, and the potential energy is 0. The total energy is always constant, has the same value all time. And at this 4 point, we discussed at the maximum x and the equilibrium point. But in general, at some point between the maximum displacement and the equilibrium position, for example, at this point, we will have that the object may have some kinetic energy and some potential energy. But if you sum up these two terms, it means that if you sum the value of the kinetic energy and the potential energy, you will get the total energy, the same total energy at all time. Okay. We can also explain this in a tabular form, as in this table. At t equal to 0 at the initial time, if we assume that, or if we place the object at the maximum displacement at t equal to 0, so we have x equal to a, and if x equal to a at the initial time, if we start the motion with v equal to 0, it means that initially the object is at rest. You will have the acceleration equal to the minus omega square a, the kinetic energy is 0, and the potential energy is maximum here at the initial time. At the 1/4 of the period, if we look back at this diagram again, at this point, is the one-fourth of t, one-fourth of a period. You can see that this is the one-fourth, this is the half of the period, and this is the third of the fourth of the period, and this is one period. Okay, so we may write this is the time here is t is equal to 0, t is equal to big T over 4, this t is equal to t half of t, this t is 3/4 of t, and this is one period. Okay, so if we look at the table again, you can see that at t, at the 1/4 of the period, the object is at the equilibrium point. The velocity is maximum but point to the left, to the negative direction. The acceleration is 0, the kinetic energy is maximum, and the potential energy is 0. And when the object moves to the maximum displacement again, but on the left of the equilibrium point, the time is half of the period. Velocity becomes 0 again. Acceleration is positive, is plus omega square a, because now the acceleration points to the right, which is we define as a positive direction. Kinetic energy is 0, potential energy is maximum, and you can follow this to the 3/4 of t and 1t. You have to resolve like this, and in general we have the relation between t, x, v, the acceleration, and the kinetic energy and potential energy like this.